The renormalizations in the supersymmetry's importance, especially the some supersymmetry conserving parameters and also supersymmetry Viking parameter. Such renormalizations should be applied to because applied to such a minimal supersymmetric model in the supersymmetry theory because there are two different scale. Some supersymmetric parameters, especially the soft term, which is some explicitly supersymmetric Viking parameters inserted in the some higher scale, but some observable quantities is the task can be tested in the sub electroweak scales near the electroweak scale. So such as some subsystems will be evolved such as some effective standard scale. So there are some algae evolutions of the such parameters, especially the soft parameters. And there are some of the low factor around Q0 through Ramchat factors will be multiplied from the loop. And there are some universality we discussed in the last videos. Such as some universalities means that there are no additional variable mixing and then no additional speed violations rather than the standard model to avoid the dangerous some additional variable mixing or speed violations which can be concerned by the current experiment. And such a some universality, such as no variable mixing and the speed violations are still guaranteed in the such a low energy effective field theory with some approximations. So in this video, we will discuss about some of the algebra evolutions of the many parameters in the supersymmetry theory. So the first one is the evolutions of the gauge coupling. C1, C2, C3, which corresponds to the U1, SC2, SC3 gauge symmetries of the standard model. Such as gauge coupling evolutions can be confirmed by the beta function or flow equations in the renormalization group. Such a beta function is defined as some dt, where the t is some log scales of the some energy of the q at the about the Laplace point of the q geos. And by calculations of the one-loop diagram, the beta functions for the gauge couplings are given by the such a form. One about the 16 pi squares is from the loop, and the such beta functions are proportional to the g cube, and there are coefficient b. Such a b is determined by the sum of the model. In the standard model, the coefficient for the G1, G2, G3 is given like that, and for the MSR sum, the coefficient is large than the standard model because there are additional superparticles that loops contributes to such evolutions. So for different coefficient for the each model, we can check the how the gauge couplings evolves. Some of the learning coupling constant. For simple analysis, we define this coupling constant alpha as z scales over the 4 pi. Then the beta functions of the 1 over the alpha is just given by the minus the BA coefficient of the 2 pi. So such evolutions of the 1 over the alpha for the some specific energy scale can be drawn like that. And in the MSS sum, the gauge coupling U1, SC2, SC3 are mixed at the some specific energy scale. It is called the unification mass scale and is called the grand unification scale. So gauge coupling for the U1, SC2, and SC3 meet at such a unification mass scale. So that is our first discussions about the evolution of the gauge coupling. And the remaining things is some superpotential parameter, which is a supersymmetry conserving thing. And finally, we will discuss some subparameter, which is explicitly supersymmetry Viking parameter. The superpotential parameter case, we can write the superpotentials with the linear, quadratic, and the trilinear coupling term. And the beta function for the coefficient for the linear, quadric, and the trilinear coupling form, such a beta functions can be written like such a general form. And actually, each coefficient is proportional to the itself. For example, R is proportional to the L with some different index for because there are Li, and there are Lj. And the M quadratic coefficient is the proportional to M itself, and the Y is also Y itself. And there are some coefficient gamma, which called the anomalous dimension operator. Such anomalous dimension operator can be obtained by this calculation the loop factors and the superpotentials parameter. So by using this better functions of the coefficients for the superpotential, we can obtain the evolution of the superpotential. And I want to discuss about some soft parameters, some supersymmetry breaking. There are three types of the soft system: gauge normal systems, and the two linear coupling scalars, and the bilinear scalar coupling, and the scalar scale system. And similarly, we can assign the beta functions of each types of the soft system. And in the subsystem case, the beta functions is some complicated form. Beta functions of the subsystem as functions of the subsystem and the superpotentials, coefficients, and the gauge coupling. There are three types of system, M, and some coupling, and scalar mass, and the superpotential parameters, and gauge coupling. Such a complicated forms of the beta function for the subsystems are coming from the supersymmetry non-renormalization theorem. If the supersymmetry is conserved, then the beta functions of such a supersymmetry conserving parameters are proportional to the itself. Already we saw in the some gauge coupling case and also superpotential case. But for the supersymmetry breaking term, like the subsystem, such a supersymmetry non-renormalization theorem is not applied for such a supersymmetry breaking term. So beta functions of such a supersymmetry breaking parameters are proportional to those also others parameter. So it's to make such a complicated forms of the beta functions for the subsystem. So I want to talk about some three different types of the supersymmetry breaking, such as subsystem. The first type is the gauge mass term. So the beta function for the gauge mass term is a function of the gauge coupling and also the gauge mass. And there are very important point. Such a coefficients in front of such a beta functions is the same with the gauge coupling. So they are a very similar form. So that is the beta functions for the gauge mass, and that is the beta functions for the gauge coupling. And such a coefficient BA is the same with the some given model. So it means that the some quantity ratio between the gauge mass and the gauge coupling scales is a scale independent quantity by the chain rule is given like that. And by using the beta function for the gauge mass and the beta function for the gauge coupling, two terms exactly cancelled out. So such a quantity, MA with the GA scale is a scale independent quantity. So we know that some gauge couplings are unified at the GT scale. So we can know that there are some specific gauge mass at the GT scale, and there are because such a ratio between M and the G scales are constant over the scale. So such a ratio between the M and the G is the same. With at the same with the ratios at the GOT scale. So there are some gauge mass unification condition. So gauge mass should satisfy such conditions. M over the G scales should be the same ratio. And the second side of the subsystem is a scalar coupling. There are two types. One, the trilinear coupling, like as some Silcock and the Higgs, and also C. Laptons and the Higgs, and also two Higgs. in this case, as all the component field, not the shape field. And there are some approximations such as trilinear coupling is proportional to the Yukawa matrix for no Blivers mixing. And the Yukawa matrix has only the non-zeros for the third family, but that such a third family component is significant as some approximations for simplicity. And also beta functions for such as scalar coupling sum, trilinear and bilinear, so also functions of the all the parameter, subsystem, superpotential coefficient, gate coupling, because the subsystems cannot apply, we cannot apply the supersymmetry non-renormalization theorem for the such a subsystem. Also, binary, the binary types is scalar scaled mass, so we can find such a data function for this parameter. And it's also complicated functions of the subsystems and the gauge coupling, because that does not apply to such a theorem. But there are two different scalar scaled mass for the Higgs and the C-parameter scalar constructor. So the point is because supersymmetry non-renormalization theorem is not applied to the such a subsystem. So also especially the other subsystem except the gauge mass term, such as scalar coupling term and the scalar mass terms has some complicated form of the functions for the beta function. So if there is a gauge mass terms and the input scale, then by the RG evolutions in the beta functions, then other subsystem, some scalar coupling and the scalar mass term can be appeared by the RG evolution if the gauge mass terms are inserted at the input scale. And at the electroweak scale, such as subsystems will be appeared. So the point is the gauge mass terms is dominant source of the supersymmetry ranking. That is some of the results of the RG evolutions of the subsystem.